So today I talk about a recent study on empirical based method for one-bit matrix completion. So this is the abstract. So one-bit matrix completion is a problem to predict unobserved entries of a binary matrix. So suppose we have a matrix. For example, this is a matrix of movie rating. So each row corresponds to a user, and each column corresponds to a movie. And for example, the user 1 watched the movie 1, but he didn't like it, so this is 0. But the movie 2, he liked it, so it is 1. So in this way, we can obtain a binary matrix. But of course, we cannot watch all movies, so this matrix is only partially observed. So if we can predict these unobserved entries accurately, then it is useful, for example, for recommendation system. And also such binary matrix setting appears, for example, in network analysis and other problems. So for this problem, we develop a method based on the idea of empirical based method, which is a Bayesian method, but the prior is estimated from data. So by using this, we develop a method algorithm for this problem. And the motivation, the idea comes from what is called Efron-Morris estimator for a normal mean matrix. I explain the detail later. So I have been working on a kind of extension of this Efron-Morris estimator from when I was a student. So this estimator has a good property that it works well for low-rank matrices due to the property of singular value shrinkage. So I explain the detail now. So I first start from what is called Stein's paradox in classical statistics. So suppose we have an observation x, which is a Gaussian random variable, and p dimension, and the mean parameter, mean vector, is mu, and covariance is identity. This is a very, very fundamental problem. But for example, if you consider general statistical model, asymptotically, in regular cases, asymptotically, as MLE is distributed with Gaussian. So this problem is a kind of canonical setting for parameter estimation. So in this setting, we estimate the mean vector mu based on x, and by using a quadratic loss, this one. So I mean, we consider mean squared error of estimator mu hat. So in this case, of course, the MLE is x itself. So, and I think intuitively, it is enough to use x as an estimation of mu. And actually, we can show that this MLE is minimax. I mean, it minimizes the maximum risk over possible values of mu. But in 1956, there was a paradox by Charles Stein. He showed that if the dimension p is larger than or equal to 3, this MLE is actually inadmissible. Inadmissible means there is another estimator that is exactly better than MLE. So this inequality holds for any possible value of mu. So this is the inadmissibility of MLE. So this is I think this is counterintuitive. So this is called Stein's paradox. So because MLE is inadmissible, there is an estimator that is exactly better than MLE. So that is called shrinkage estimator. And I think the most famous example is this James Stein estimator given by this equation. So you can see that we have a 1 minus something before x. So this coefficient is strictly smaller than 1. So the situation is like this. So this is origin. So this is a p-dimensional space. So this is origin. This is observation x. So instead of using x as an estimate, we shrink x towards the origin. And this is the James Stein estimator. And after some mathematical proof, we can show that this red one is always has a smaller mean squared error than x itself. So this is Stein's paradox. Okay. This is an example of a risk function that is a mean squared error. So here the x-axis is the norm of mu, and the y-axis is the risk, that is a mean squared error. So this black line is the MLE. So you can see that this is a 10 dimension. So MLE has a mean squared error 10 for any possible value of mu. This is a constant risk. But for the red line, this is Jamestown estimator. So you can see that this red line is always smaller than black. So in this sense, the red Jamestown estimator is better than MLE. So yeah, so this morning there was the E introduced the minimax rate. So here, this is not asymptotic. So this is a minimax in finite sample. Yeah. So without using asymptotic, already in finite sample, we have a dominance like this. And the risk reduction is large if the mu is close to origin, because we are shrinking towards the origin. Okay. So there is a extension of this Stein's paradox to matrix case. So suppose we have a P times Q matrix X, and each entry of X is a Gaussian random observation of M. I mean, we have an unknown matrix M, but each entry of M we can observe with Gaussian additive noise. So that is X. And the noise is independent. So in this setting, we are interested in estimating M based on X. Okay. For example, if you consider linear regression with vector response, I mean, linear regression with several responses, then the problem is reduced to this form after sufficiency reduction. Okay, so in this setting, we consider estimation under provenance loss, which is just a quadratic loss for matrices. So for this setting, Efron and Morris proposed this estimator. So we call it Efron-Morris estimator. So actually, if the Q is equal to 1, this reduces to the Jamestown estimator. So in this sense, this is an extension of Jamestown estimator to matrices. And after some calculation, we can show that this estimator is actually minimax and dominates MLE. So the mean squared error of this estimator is always smaller than MLE. Okay. And this estimator can be understood as doing a shrinkage of singular values. So after singular value decomposition, we can confirm that this estimator has this form. I mean, each singular value of Efron-Morris estimator is a shrinkage version of the singular value of X. And this is a shrinkage factor. And you can see that this shrinkage factor is very, very similar to the factor in Jamestown estimator. So this is the Efron-Morris estimator. Okay, so for example, this is the case of 10 times 3 matrix, and the x-axis is the second singular value, and the y-axis is the mean squared error. So you can see that this red one is Efron-Morris estimator, so it has a smaller risk than black and blue. So black is MLE, blue is Jamestown. I mean, we can vectorize matrix to, in this case, we can vectorize the matrix to 30-dimension vector, and then apply Jamestown shrinkage. That is also minimax, but that is not so good. So compared to blue, red is much better because it has the effect of shrinking singular value. So this Efron-Morris estimator is good for low rankness, I mean singular value structure of a matrix. So it is compatible for the structure of a matrix space. Okay. So if the second singular value is small, then we obtain more risk reduction. And even if sigma 2 is large, we still have risk reduction because of the third singular value is 0. More pronounced in this case. So this is a rank 1 case. So both second and third singular values are 0. So only the first singular value is non-zero, which means the matrix is low rank. So in this case, you can see that even if the first singular value is large, we have a constant risk reduction because of that second and third singular values are 0. Okay. So in this way, this Efron-Morris shrinkage is effective if the matrix M is close to low rank. We obtain a good risk reduction for low rank case. Yeah, so I think in many cases, we encounter matrices close to low rank. So in such case, this type of shrinkage is effective. So this is the singular value shrinkage property of Efron-Morris estimator. Okay. And I have been working on some theory related to this Efron-Morris estimator from when I was a student. So recently, we obtained this property. So actually, the Efron-Morris estimator is better even in terms of matrix valued loss function. So yeah, I don't explain the detail, but we can show this inequality. So, you know, if you take trace of this, then that is provenance loss. But even before taking trace, we can show this inequality in terms of matrix order. So this is a recent result. And relatedly, we applied it to non-parametric estimation, so like a Sobolev space for vector valued function. So actually, we can show that this F-Romulus estimator can be used to do a adaptive estimation in non-parametric function estimation. So this is the second one. And the third one is the Bayesian theory. So yeah, so I don't explain the detail, but this prior we developed in this paper. So we can show that this prior satisfies a property called superharmonicity. So I think in this morning, the Martin introduced the harmonic function on graph. So this is a superharmonic function. So such a superharmonicity is good for Bayesian minimax estimation. So yeah, so the detail is in this paper. Okay. Yeah, so far I have been working on extension from vector to matrices. So I have been interested in tensor case like this. But to my knowledge, even the definition of rank or singular value for tensor is not so clear. It's not so established compared to matrix case. So I haven't done any concrete result. But it would be nice if we can do, sorry, I didn't explain, but F-Romulus estimator can be derived as an empirical based estimator. I explain the detail later. So hopefully such kind of argument may provide a good estimator for tensor as well. So this is a future work. Okay, so now I come to today's topic. Okay. So matrix completion, the famous example is the Netflix problem. I think this was popular in machine learning community before the deep learning appeared, I think. So yeah, so as I explained in the introduction, this is a matrix of movie rating, and we want to predict these unobserved entries to do a movie recommendation, okay? And many studies investigated this problem from theory and also algorithm. And the key assumption here is that the matrix is assumed to be low rank. Of course, if we cannot assume any structure in this matrix, then it is impossible to estimate these unobserved entry. So we need some assumption. And empirically, it has been found that assuming a low rankness of this matrix is very, very useful to do a prediction of unobserved entries. So this is matrix completion. So here the movie rating takes integer value. But in practice, we often encounter a situation where the response is only binary. So for example, in the website, we click or not click. Or we can just say, I like it or I don't like it. So that is more intuitive and more popular way to do an evaluation of rating of something. So in such setting, there has been some studies on doing imputation in this setting, and that this problem is called one-bit matrix completion. So here I consider this problem and using the idea of F-Romulus estimator. This is a problem setting. So suppose the binary matrix is Y. So each entry of Y is 1 or 0, binary vector, binary valued. So each entry of Y is a Bernoulli random variable with the success probability given by f of Mij. So we have a hidden matrix M. So based on the hidden matrix M, each entry of Y takes value 0 or 1. Yeah, that is the setting. And for the link function f, we can consider several possibilities. So one is this probability link, and another is this logistic link. So this is a typical choice for example, in GLM. So if we do a binary regression, we often use this type of link function. Okay. So then the omega is a subset of this direct set. So this is the index of observed entries. Okay. So in this setting, we are interested in predicting Yij for Ij not in omega. So only observe Y for omega. So based on that observation, we want to predict Yij for unobserved entry of Y. So this is the setting. Okay. So again, so to do this, we need some assumption, and the key assumption here is that this hidden matrix M is assumed to be low rank. So by using this assumption, we can derive some algorithm to do prediction of Y. This assumption of low rankness of M appears in another field. For example, in psychometrics. So in psychometrics, there is a theory called the multidimensional item response theory. Okay, so in this multidimensional item response theory, the assumed model looks like this. So let's say we have a data of examination. So each row I is a student, and each column J is a problem. And it shows, for example, this student solved this problem. This student could not solve this problem, such a binary matrix. In this case, for such data, this model is used in this theory. So we assume a hidden vector AI and Bj for each student and each problem, and the success probability of each entry is given by this function. So this is the setting of a multidimensional item response theory. And you can rewrite this model to this form by introducing a matrix M. Then you can see that this matrix M is low rank, and the rank is equal to the hidden dimension of this ability and difficulty. So this is one example of why low rankness appears in this problem. So conventionally, so the previous studies developed algorithms based on this approach. So by formulating the problem to optimization like this. So this is a constraint maximum likelihood. So by using some constraint capital C, we maximize this log likelihood under this constraint. And this constraint, there are some studies, they use different kind of feasible set C to express the low rankness of M. But anyway, so this is a usual setting to solve one-bit matrix completion. So by using this, we can estimate M. Then by using that estimate M, we can predict unobserved entries of Y by using this formula. So this is the previous approaches. So here you will use the empirical based approach. So empirical based is a Bayesian approach in which we estimate prior from data. So this is a general formula, general setting. So suppose we have a prior pi for theta, which is indexed by hyperparameter alpha. So based on observation of Y, we estimate hyperparameter alpha in some way. For example, by maximizing marginal likelihood. So by using this, we can impute this alpha hat to the prior theta. Then we can do Bayesian prediction of another observation Z like this. So this is a prediction in empirical based way. So here so this is actually the ephemeral estimator can be derived as an empirical based estimator. So yeah, so for this setting, we put this prior for M. So this means, this is a notation for a matrix Gaussian distribution. But the meaning of this is given by this. So each row of M is independent and identically distributed with Gaussian distribution with covariance sigma. Okay, so this is a prior on M, and we estimate this sigma, hyperparameter sigma, by using a moment matching, by using a property of inverse Wishart distribution. So we can estimate the sigma in this way. So by using this sigma hat, we can estimate M in a Bayesian way, I mean posterior mean. So that is actually equal to ephemeral estimator. So in this way, ephemeral estimator can be derived as an empirical based estimator by using this prior form. So yeah, so we expect that this kind of argument is effective for low rankness. So we use this argument for matrix completion. Yeah, so the derivation is very, very similar. So we put the same prior, but here for estimating sigma, we cannot do it in closed form. So we do it in by using Monte Carlo EM. So this is a variant of EM by using MCMC. By using this, we can predict unobserved entries of Y by using this Bayesian predictive distribution. So yeah, so in this way, we can predict unobserved entries of Y with probability. So this is the setting, and you can see that this procedure does not require any parameter tuning. So this is a technical detail. So to do MCMC, we do a technique called data augmentation, but I don't explain the detail. This is an MCMC technique. And by using this, we can do Monte Carlo EM. So in E step, we do give sampling, and in M step, we calculate posterior mean. So by iterating this until convergence, we can estimate sigma by solving this maximization problem. Okay, so this is a simulation. So we consider probit case, and we compare to several previous methods, and we evaluate by using Hellinger distance for unobserved entry. So this is a setting. This is the first result. So we consider 1,000 times 100 matrix with rank 5, rank 5. And only half entries are observed. Okay. So in this setting, this is the result. So we can see that our method has better accuracy than others. Yeah. So actually, I didn't expect it so much, but it was good that this method is better than existing methods in terms of accuracy. So this is a performance with respect to the P, which is the number of rows. So this red line is the proposed method. So we can see that this empirical base works well, especially well if P is large. So if P is large, that is the matrix is more skinny, then this empirical base method works well. Yeah. Actually, F-Morse estimator has a similar property. So this is compatible with such property of F-Morse estimator. Okay. And this is a plot with respect to rank R. So yeah. So of course, if the rank is large, then it is more difficult to predict the matrix. So it is increased, the accuracy error is increasing with R, but anyway, so the degradation of performance is not so bad compared to other methods. This is the x-axis is the proportion of observation. So of course, if we observe more, then it is more easy to predict. But anyway, so for each value of proportion, we obtain a stable performance here. So finally, we consider application to real data. So sorry, this is a bit busy slide, but for real data, we mask some observed entries like a cross-validation and evaluate the prediction performance of this masked entry from observed entry. So yeah, so we evaluate by accuracy and cross-entropy loss. And also, to evaluate the calibration property, we calculate this expected calibration error, ECE. Okay, so this is a benchmark data, movie lens data. And actually, the performance is almost the same for 4 methods. So it might be related to Ishida-san's talk, so the performance may be saturating. So yeah, you can see that all methods attain almost the same accuracy. So anyway, so we can say that our method is not worse than existing methods. So this is the first result. And the second one is a joke data called gesture data set. And in this case, we found that, interestingly, in this case, the P is much, much larger than Q. So in such case, we confirm that empirical Bayes works well, computationally more efficient in such skinny case. Okay, so in this way, we developed an empirical Bayes method for one-bit matrix completion motivated by a Morris estimator. So yeah, so it would be nice if we can do some theoretical guarantee and also efficient implementation. And also, again, it would be nice if we can extend to tensor case. Yeah, that's all. Thank you.
Okay, thank you for the talk. Is there any questions from the audience?
I would like to ask a question. So if you assume that the matrix M comes from some matrix valued Gaussian distribution, why it is low rank?
Thank you. So the intuition is if the data has a low rank structure, then this sigma hat becomes also close to low rank because we have Y transpose Y here. That is one understanding.
You first assume that the data is low rank. That's why even if the capital M is sampled from some Gaussian distribution with identity matrix, it's still low rank. Because the covariance matrix sigma is low rank. I mean.
Yeah, if sigma is low rank, then M is also low rank. Yeah. Okay. Yeah, so this procedure is kind of adapting to the low rankness of M in this way. Yeah.
Thanks for the interesting talk. Can I ask about this one-bit completion versus a more general case? Say you have like rating from 0 to 9. Yeah, so how does this, so effectively the procedure doesn't assume the one-bit matrix itself is low rank, but the Mij is low rank that go through this Bernoulli in F. So what is the, does this make the accuracy or like accuracy measure more like worse or make the problem more difficult for this one-bit problem instead of just have a general scalar valued entries?
Thank you. Yeah, so I think in general, one-bit is more difficult because we only have a quantized observation. Yeah, so if we observe Y from Gaussian distribution, that has more information about N. So in the one-bit case, we only have a kind of a thresholded value of N through the logistic or probability link function. So there is a theory showing a minimax lower bound. So it says that such a thresholding reduces the information.
Yeah, thank you for the nice talk. So for the rank R, I'm wondering how you choose the optimal rank R. Do you learn it or as consider as a hyperparameters?
Thank you. So in this setting, R is estimated implicitly. So I would say the effective rank of sigma hat is almost R. I mean, this is this procedure. The R rank is not explicitly estimated, selected, just implicitly through this prior adaptation has an effect of rank selection in a Bayesian way. So sorry, does it make sense?
Okay, so not choose by manually. It's depend on the posterior distribution.
Yeah,
it's
kind of,
automatically pruning.
Exactly. So this procedure is free from such tuning. So that is one advantage, I think.
Okay. Okay. Second question about regarding this application, one-bit matrix completion. what's the prior distribution for the latent factors A and B?
Okay. So in our method, we don't consider this form. But yeah, so there is some method to think prior on this A and B.
Yeah.
Is it what you mean?
Yeah. I'm wondering what's your assumption of prior distribution over A and B?
Okay. That's a good question. So in our case, the prior is given directly for M. But yeah, as you say, it would be interesting. In this A and B parameterization, what is induced prior for A and B? That is an interesting problem.
I see.
But yeah, thank you.
Yeah. Thank you.
So thanks for the nice talks. I have two questions. So one is, so as far as I know, so for this binary matrix factorization, one of the innovations was actually positive unlabeled low-rank matrix factorization. Because one is observed as positive explicitly, but 0 is unobserved, basically.
Yeah.
So then PU learning really matters in this scenario. So can you
Yeah,
somehow
yeah.
incorporate that kind of taste in your framework?
Yeah, actually, from your talk, I noticed that. So I haven't thought about it so far. But yeah. So it would be interesting to incorporate such technique in this setting. Yeah. So yeah, thank you.
Great. So then another thing is maybe Chibin has to ask it, but can you extend it from matrix to tensors? That's more important in practice.
It's possible to test, of course.
What do you expect, like as a challenge? What do you expect if you consider tensor case or tensor train? Or
Yeah, I'm not so very familiar to tensor theory. So I think one topic is, Ephron Morris is minimax even in finite sample. That is a very strong statistical property. So as far as I know, I don't know such a tensor estimator with such strong property. So if we can derive such, of course, for example, if we just vectorize the tensors, then we can do that. But it would be nice if we can do a truly tensor type shrinkage that works exactly well. So this is a very ambitious future work for me. Yeah.
Was it already explored, or is it an unexplored topic?
Maybe not so explored because I have to say that this shrinkage estimation is a very classical topic. So I'm not sure if somebody has attained.
That's good news.
From theoretical point, maybe not explored, but many empirical algorithms already extended.
But if you could support those empirical methods with some theory, that would be great. Thank you.
Thank you.
May I ask one more question? Follows Sigma Sensen's question. Is there any research about a 2-bit matrix completion where we have PNU? Because in your example, you mentioned that the user really click, I like this movie or I don't like this movie. But if originally it's from 1 to 5 or 1 to 10, there should be 3 values. Because if user click, I like this movie, that means user really likes this movie. If it's I don't like, this really I don't like. For a lot of movies the users watch, maybe they will not express any like a strong positive or strongly negative opinion. Then that should be -1, 1, and 0. 0 may mean it's unobserved, or maybe it's unobserved. Maybe the user has not watched this movie, or the user watched the movie but doesn't have any strong opinion. That's very interesting. Have 2-bit.
Yeah, so I think that in statistics there's an ordinary regression. So if here this is just a binary, but as you say, we can do, for example, 3. So we have a 2 threshold.
Yeah, but then the math can be more difficult. This is Bernoulli distribution, but if it's 2-bit, like -1, 1, and 0, we need some very maybe special model.
Actually, that is a bit straightforward. I mean, by manipulating this some MCMC, we can do an ordered case of probability regression, logistic regression. Okay. So yeah, thank you. So I think this procedure can be adapted to such case as well.
I see. Yeah. So your algorithm can be easily applied to such case. Just we modify the distribution of YIJ, right? It's no longer Bernoulli distribution.
Yes, yes, yeah.
Okay, thank you.
Thank you.
Okay, so it's time to move on to the next talk. Let's thank Dr. Matsuda again for the interesting talk.
Okay, hello everybody. So first of all, I'd like to thank Takashi Ishida and Wenkai for leading that grant that allowed us to be here. It's really nice to have this get together, and I'm delighted to give a talk here on Bayesian inference and design. So it's a bit of an overview talk. So first, I'll introduce my research program, so what drives my research and what are the big questions that I'm asking. And then I'll zoom into three different recent projects. Probably time constraints mean I can't quite cover the last one, but we may discuss informally later. Right, so the big question that I'm asking myself is, how should an agent learn and act in a world it does not fully understand? So this involves like two questions, like the learning, so what to do with data that the agent observes, and the acting, which means both like data collection, also acting to achieve something. And the crucial bit is, well, the agent operates in a world full of uncertainty, so it doesn't quite understand the world too well. The applications that I'm interested in are like in science engineering. So I would like to use these agents or the learned methods in order to do something interesting in science. So to assist us with doing science, or to assist engineers when developing new products. So the big question then kind of rests or like splits into three pillars. So the first one is on learning and uncertainty quantification. The second is actions for system understanding, where here I means like essentially actions to better understand the system, so like experimental design. And then here, so this is more the science part, while here the actions for system design is more the engineering part. So here we don't really necessarily aim to better understand the system. We just want the system to do what we want it to do. So we want to achieve a certain goal. So for each of these pillars, these are some kind of projects that I have been working on, or that I'm working on. So here for learning and uncertainty quantification, I've been working on Bayesian inference for simulator models and inference for energy-based models. So the common part here is for both of these models, the likelihood function is intractable. So simulator-based models are models that we can simulate data from, while the energy-based models are like unnormalized models where you don't know the partition function. So recently, I've also become interested in learning and inference with misspecification, which is, of course, quite important because it relates to this world that we don't really fully understand. So we may assume a model, but the model, reality does not correspond to the model. For the actions for system understanding, I've been working on a Bayesian optimal experimental design. And this is like a sequential decision-making procedure that needs some kind of utility function. And the utility function that we have been using was actually the mutual information, or the expected information gain, which then led to more questions or more research problems, namely how do we actually estimate that quantity efficiently? Because mutual information estimation is not trivial. One has to work to estimate it. Then for system design, this is like my most recent pillar that I added to my research program. So we have been working on using also Thompson sampling and RL together with risk management to solve some kind of design problems. So the risk management is important because, again, this relates to this goal of operating in a world that we don't fully understand. So for instance, we may take an action for which the expected reward is great, but because we have uncertainty about our world that we're operating in, we shouldn't just look at the expected value, but also be some like risk sensitive. So these are like the methods that I've been working on, and then together with domain experts, I'm currently working on topics related to antibiotic resistance and also in systems biology. So antibiotic resistance falls like into these two categories, where we need to like calibrate the model that they have been coming up with, and then we are using experimental design to drive new research in that domain. And for systems biology is more this pillar, even though, well, this one is also important. So what is maybe interesting is all these pillars, they interact with each other, right? Like once we acquire new data, we use it to learn and quantify the uncertainty. And then our notion of what we know about the world then drives new experiments, for instance. These two also interact in the same way, and these two also interact. This is kind of the classical exploration versus exploitation trade-off, where here perhaps you would like to more exploit, where here we are very happy to just explore. Right, so in today's talk, with the rest of the time I have, I'll discuss a project on the simulator models, so Bayesian inference for simulator models, then a project here for Bayesian design, and if ever miraculously I have some time left, I'll also talk about regional information estimation for this second pillar. Right, so for the first project, so this is based on a recent paper with some collaborators from Greece. Right, so indeed, both in science and engineering, models are used all the time. So it's kind of a model-driven world. And quite often in these domains, the model is described or prescribed in terms of a generative process. So this means like it is, for instance, a digital twin, or like just a simulator of the physical world. So here in this little cartoon, we have like a model or a cartoon of a cell, where we model how energy is used by the cell, or how then genes are expressed, etc. And this is, of course, just a model or a digital twin of the reality that we're then using to learn about the real world or to take decisions in the real world. So mathematically, the simulator corresponds to the mapping that I denote here by G, that takes two quantities as input. One is theta, which are the parameters of the model. And the other one, or the other input is like randomness or noise. Think it's like the seed of the computer program that you're running in a stochastic simulator. We also have a prior on our parameters. So the goal is model calibration. Quite often before we can do something with the model, we need to calibrate it with real data. And in the Bayesian framework, what we then need to do is to compute the posterior here of the parameters given the data. The issue is really if the model is specified in this kind of generative way, the probability distribution of any output y given theta is well defined. It's just like the push forward of p of omega. However, become like getting a closed form expression for it or computing that probability measure is of course really hard, right? We have to compute the probability mass of the inverse image, and G, the simulator, is typically not known in closed form, so we can't possibly compute the inverse image. So this means then the probability distribution is well defined, but typically intractable to compute. And because, well, this is intractable, it means the likelihood function is intractable, and hence getting the posterior with classical methods like MCMC or variational inference, etc., is intractable. Right, so a popular approach to deal with this intractability uses machine learning surrogate models. So it exploits the idea that we can generate from the model data y. So we just sample values from the parameters, pass it through the simulator, and then collect the data set. And then we use that data set to model the relationship between the parameters theta and y. So we can go both ways. So either we learn to predict theta from y or y from theta. In the first case, we approximate the posterior. In the other case, we approximate the likelihood. So what is quite popular these days is to use flow models, possibly with some kind of learned summary statistics to reduce the dimensionality. So this works quite well. Some issues there are that, well, for flexible models, we need a lot of training data, but sometimes generating that training data is computationally expensive because you need to simulate it. So sometimes the simulators, they may take 24 hours to run. So even if you have a large clusters of computers, you don't get the training data that you need to train highly flexible models. Moreover, they're also a little bit brittle. So somehow the surrogate models, they learn this may be so flexible that they work very well when all the assumptions are satisfied. But as soon as there is a bit of a change, we have like an out of distribution problem that we have seen already. And then things don't quite work that well. So here we have like a simple illustration of this issue. So what we want to, or what the setup was like a mixture of Gaussians just with two modes. And the first row here is like a simple problem, mainly just 2D. And MPE, base flow, and FMPE are three recent methods for like approximate Bayesian inference in this setting. MPE means neural posterior estimation. Base flow is base flow, and FMPE is like a flow matching based method. So what we see here is that, well, things typically quite well. So both in the low data regime as well in the high data regime. And if it doesn't quite work well if you have little training data, you just increase it and then it works well. So what we then did is like, we just increased the dimensionality. So instead of 2D, we have 10D, which is not too high, but in this setting, in simulation-based inference, it's a reasonable problem. So here we see that what worked well actually doesn't work well anymore. So for base flow, just it doesn't scale that well. Well, here it didn't work either. Here it's also not too good because most of the data is just on one mode. Then even if we increase actually the data, or what the solution would be just to increase massively the training budget. So here, this is like 50,000 data points instead of 1,000 data points. In some cases, even if you increase the budget, say from this case to this case, it still doesn't work too well. Another scenario that we tried out is like when you have uninformative dimensions. So here, the observed data was 10-dimensional, but actually only two had a relationship with respect to the parameters. So some of the dimensions were not related to the parameters, so they were like distractor dimensions. And then also actually things started to break quite easily in the existing method. So the summary is like things work quite well in the standard setting, but performance deteriorates quite quickly when we have higher dimensions and then when we have distractors or some kind of change in the data generating process. So what is the problem that we would like to solve? So we assume we are given our generative model, a prior on the parameters, some data, IID, and then as well as a distance function that kind of represents the geometry of the space. The goal is to generate samples or from the posterior or an approximation of the posteriors so that A, we are more efficient, so that we don't need to increase the number of data points as drastically as here in order to get the performance boost when things don't work that well. And the second goal is also to be more robust with respect to these uninformative dimensions. Right, so our approach leverages a method that we developed some time ago, which is called robust optimization Monte Carlo. So the way it works is that we using a notion of the likelihood function as a bit of a generalization of the standard likelihood function. So what the generalization is that it's the probability that the distance between the observed data and simulated data y, when using parameter theta, that this distance between the two data sets is less than epsilon. So that's the generalized likelihood function. So we can also write this as in this form here, when we just use like the law of the unconscious statistician, because y was generated according to this process. So we can take the expectations just over p of omega. So the C epsilon is here the set of tuples omega and theta, such that the distance of the simulated data when using parameter theta and the random seed omega, that this distance of the simulated data and the observed data is less than epsilon. Then, in order to deal with this expectation, what we do is we just take a sampler average. So it is now just a sample average of these indicator events, where the C epsilon I are the crucial quantities here. So we call this the acceptance regions. So this is all the thetas for which, for a fixed seed omega I, the distance is less than epsilon. So the idea in robust optimization Monte Carlo is now we are obtaining an approximation of the likelihood function by approximating these acceptance regions. Because once we know these, right, we have 4, and which is a reasonably good approximation to 3. So the hard problem here is the characterization of these acceptance regions. So once we know them, the problem essentially is solved. So what we do to approximate these acceptance regions, what we find is at the points of minimal distance. Think of like it's the central point of these acceptance regions. And to do that, we solve this optimization problem. So for a given seed, omega I, we just find the theta that minimizes the distance between the simulated and the observed data. And once we have that, we then build a local model around that point. Local because, well, epsilon by assumption is small, so we can't just build a small model around it. In our case, actually, we just used a small hypercube centered at this point here. So the key thing is that, well, these optimization problems are deterministic because we fix the seed. And assuming differential simulators, which we assume here, it can be solved really efficiently by gradient descent. And these gradients are really key to scalability because we know optimization works very well once we have gradients, and gradient-free optimization is hard. So here we have the same kind of setup. The gradients are also used for the sensitivity analysis because they allow us to identify and filter out these distractor dimensions where there is no link between theta and the outputs of the simulator. Once we have then our approximation of the acceptance regions, what we do is we just put a uniform distribution over it and then use multiple importance sampling to get the posterior samples. In case of like multiple observed data points, we would form a mixture distribution. Here I skipped the details, but they are in the paper. Additionally, we use also checks to increase the efficiency. So here we have some results. So it's like a simple mixture of Gaussians benchmark. And the plots here are like success frontier plots that show like the minimal runtime that is required to achieve a certain accuracy. So here we have dimensions versus the runtime needed. So we see that both without distractors, so at one point as the dimensionality goes up, the existing methods just take much more time, while ours is the red line here, which is kind of constant almost, just thanks to the use of the gradients. With the distractors, we have kind of the same picture, really just the other methods, they start to deteriorate much quicker, while ours, has almost constant runtime. Here is like one example on a popular benchmark. So it's like the inference problem is just 2D. So the true posterior has kind of this 2 half-moon kind of shape where the marginals are looking like that. So here we have time versus a performance measure, which is kind of saying, yeah, how similar the inferred posterior samples and the true posterior samples are. And we see that, so the best thing is 0.5, so undistinguishable. And we see that, well, the existing methods are kind of up here, while with our gradient-based method, we are both much faster and more accurate than the other methods. So like, yeah, 100 times speed up and much better, at least 100 times speed up and much better accuracy. Thanks to the gradients, the method also scales quite well. So here we have like an Bayesian inference problem on 784 dimensions, where we corrupted MNIST images and then tried to infer back the quant truth images together. So we show here the posterior mean together with the uncertainty or notion of uncertainty, both in case of this kind of corruption and in case of this kind of corruption, where I guess here you can't quite see it. It's not just completely black. It's just, it was like we performed like edge filtering for the data. Right, so that was the first example project. I think I have like 10 minutes left, so I won't make it at all to the mutual information estimator, but that may be okay. Right, so this piece of work is based on this paper that we published in the journal Cell Systems. So designing systems is, of course, a key task in engineering. And there again, models are used all the time. For instance, in hospitals, they are used to predict patient flow. In traffic management, they are optimized to the road networks. And in synthetic biology, they are indeed used to design genetic circuits. And there are, of course, many more applications. So their design is framed as an optimization problem. But the issue is that these models are never perfect. And this means if there's a big discrepancy between model and reality, if your design is based on the model, then once you deploy it, maybe things don't work that well. So what our approach is to this problem is that we keep track of the uncertainty that we have on the level of the models and push it through the whole pipeline so that we have the uncertainty on the level of the model becomes uncertainty on the level of the design. And then we use risk management to choose a proper design that we think balances risk and reward. So what we assume given is, again, here a stochastic generative model where theta is split into 2 kind of parameters, eta, which are unknown parameters that we can't control, and phi are parameters that we can control. So phi are the design parameters. Again, we have a prior over the parameters that we can't control. We have some data from previous design attempts, and then we have a loss function that tells us how good the design is. And the goal is to find values of phi, so of the design parameters, that are expected to work well even in unfavorable conditions. So our approach has 3 steps. The first is like use the data to update our belief about eta. Then the second step is Thompson sampling. So the way it works is, or one way to do Thompson sampling is you sample parameters from your current belief. Then you get here an objective function for that parameter value. You find the optimal design and the corresponding values in one sample, one Thompson sample. To get the next Thompson sample, you draw a new parameter from your belief, you solve the optimization problem, and then you go on like that to generate samples all the time. Here we average over omega, so we average over like the intrinsic noise in our system. Now, as the third step is then the risk management. So we have now a bunch of possible designs. So all the Thompson samples are possible designs. So what we then do is we compute the predicted loss distribution. So we push through all our uncertainty, both on the level of omega and eta, for a given design phi I, and we look at the resulting distribution, and then we choose among the phi I according to some kind of trade-off that we are willing to do. Right, here the same thing again as in terms of a picture. So we have some data, We use the data to calibrate or update our beliefs about the uncertain parameters, which were the etas. And then we, together with our target, which in this case would be oscillation in a genetic circuit, we push then through this uncertainty on the level of the parameters through Thompson sampling to get some uncertainty about what the designs could be. Then we use that uncertainty we use the uncertainty to evaluate each Thompson sampling in terms of its loss distribution. And then we look at these distributions and then pick, according to our risk sensitivity, a possible design that we're interested in. Right, so here just one example. So this is about the design of a genetic circuit. So we have like 3 elements that inhibit each other. So we have an oscillator. I guess for the sake of time, I don't explain here the stochastic differential equations. So we just have 2 parameters that are uncertain, eta, and 2 parameters that we are interested in. Fine. Design goal is having an oscillation that looks roughly like that. And the observed data that we are using is like a failed design experiment that produces data like this, so far away from our target. So in step 1, we used here a particular inference methods for simulators, but we could have used the method actually that I presented as the first project, in principle at least. So then the prior was uniform between 0 and 10, and then we see that actually the data, so this failed design attempt actually was really informative. So it allowed us to shrink the belief quite drastically, so from 0, 10 just to 0 to 3 and 0 to 0.6 roughly. Then for Thompson sampling, what we did indeed is we drew parameters from the posterior, and then we, as a loss function, we used here the loss of the Fourier spectrum between the simulated and the target trajectory. Why the Fourier spectrum? Well, in particular, we took here the absolute values. This we did because, well, oscillations might we have like an arbitrary phase shift that we are not interested in. And by working in the Fourier domain, we can get rid of that phase shift. And then when we do that, we can here show the distribution of the Thompson samples. Finally, we then compute the predictive loss distribution for all the designs. And in order to summarize the distributions, we computed 2 statistics, namely the median, the expected performance, and then the 75 quantile. So in other words, the median given that we are worse than the median. And when you plot that against median loss versus, this is kind of expected performance versus risk, we actually got a curve like that. What we expected was or a scatter plot like that. What we expected was actually some kind of trade-off, which we didn't here obtain. So in a sense, whatever is good in terms of expected performance is also good in terms of risk. So then these are the best possible designs. Mapping that back to the distribution, these dots here correspond to designs laying here. So now either one could, any design from the red area is kind of guaranteed to be good in terms of predictive performance. If you just have to pick a single one, we suggested to just take the centroid of this cluster. So how well does that perform? Well, we then kind of simulated the deployment. So here we show each row is a particular simulation under the ground truth parameter, just including the aleatoric noise. And here is time, and this is like the Gesine expression, or the value of the expression. And the goal, right, was like having four peaks in the time window. And we see that each row has roughly like 1, 2, 3, 4 bright areas. So we kind of achieved the design goal here. Here, this is for comparison what we obtain when we just work under the prior. So when we ignore the failed design, which maybe is quite, many people may do that because, right, it's a failure. But for us, even a failure is just valuable data. And indeed, by using the data, yeah, we have better performance than by not using the data. Okay, that was the second project. So I'll just skip the third one and head to the conclusions. So the big question that I'm interested in is like, how should an agent learn and act in a world that it does not fully understand? And the overall goal is to contribute to building trustworthy and uncertainty-aware agents or methods that assist us in doing good science and engineering. I split this bigger goal into, or it rests on 3 pillars. So pillar one is learning and uncertainty quantification. Pillar 2 is actions for system understanding, so experimental design or active learning. And then the third pillar is actions for system design. So I sketched or briefly introduced you a recent project for the first pillar, which was Bayesian inference for simulator models, which was based on the theory of robust optimization in Monte Carlo, where we there achieved both reliable as well as state-of-the-art performance, mostly thanks to the use of the gradients, because this method allows us to use gradients, which allows us scalability and the sensitivity analysis. The second project on for system, which was actually, this would be for 3 really. So this was the project for systems design. So there, what we did is we took a Bayesian approach. So any uncertainty that we had about the system, we propagated or pushed it through to get uncertainty on the level of the design. And then we used risk management to select among possible designs or that achieve a good trade-off between risk and the reward. What I couldn't talk about, which was like the project for the pillar 2, was this mutual information estimation. So it's like based on a theory of, a recent theory of something called vector copulas. And what is nice about it is quite naturally it enables model selection and thereby again provides robust and accurate estimates. So for those of you who are interested in that, please just ping me off during the break. That's all. Thanks very much for your attention.
Okay, thank you for the nice talk. Is there any questions?
Can I ask a quick question about the design part while you have the 5 function to optimize, while you point out the SMC ABC part? For approximate Bayesian computation, we normally choose a particular sort of summary statistics to compare. Mm-hmm. Is there an intrinsic link between the 5 we learn and the choice of summary statistics in ABC?
Right. So I guess, like broadly, your question is a bit like, well, is there a link also between these two? Yeah. It's quite a close link, really. So here, for Thompson sampling, we use this kind of objective, and for the inference, we use essentially the same objective, where instead of the target, we just use the observed data. Right. Yeah. So quite in a way, it's just the problem is, I mean, there must be a deeper connection between ABC and Thompson sampling. In terms of practicalities, we could just use the same kind of objective, where instead of the target, we just had the observed data.
Right, I see. Thanks. Thanks a lot.
Is there any other questions? If not, let's thank again Dr. Gutmann.
Thanks for everyone coming, and thanks for the nice introduction. It's a great pleasure to come back after a very long time. As Sugiyama Sensei mentioned in the morning, I have been here 7 years ago as a research intern, and now we would like to seek for more research collaboration and to explore interesting work together in the next 5 years. So to give a bit of overview of my research and relate it to statistical safeguarding program, I'm framing the talk as interpretive testing and model criticism. Essentially, I would start by talking about some machine learning problem via distribution comparison. And in the sort of like interlude, I'll talk about a specific way to compare distributions, as well as I will talk about the model assessments for generative models. And to conclude, I will also talk about some of the applications for this testing framework applied on foundation models that people are keen these days, as well as some broader scopes. So the problem I'm going to talk about is actually very simple, summarized in this picture. We have some data we want to see whether it's come from a particular model. So this can branch into two different problems. Firstly, we want to do a learning problem that we want to learn a model P that best fit our data. Also, we want to do inference or testing, while we also care about the uncertainty on the sort of divergence measure between the estimated model or the given model with the data. So there are many existing or interesting problems in machine learning that requires a specific choice of this D between P and Q. So for example, in variational inference, people normally choose KL by default, and in generative modeling, people can choose different ways to compare the generated distributions as well as the observed distributions. For example, in this handwritten digits, we may want to learn a generative model that can generate samples or the digits looking analogous to the handwritten observed digits. While what does it mean by looking the same, or in terms of distribution, they come from the same distribution, requires a specific choice of measure to compare the distribution. So I'm going to talk about this interpretable testing and model criticism for today's talk, given a very simple example on the Chicago crime data. If we have some data point in blue, like this part, and we fitted some oversimplified model here in red, we want to ask whether they come from the same distribution. And from a glance, we probably already have a intuitive answer. They may not come from a similar distribution, but we also want to proceed to say, if they don't come from the same distribution, where does the data distribution and the model distribution differ the most? So these are one particular notion of interpretable feature, and there are different ways to develop interpretable feature extraction via the testing framework. I'll talk about it in a bit. So how do we choose the measure or divergence to compare distribution P and Q? I'm going to mention two popular family of divergence measure, starting with the phi divergence, or sometimes people call F divergence in machine learning. So the divergence between P and Q is through the expectation of some convex function on the ratio between P and Q, on the density ratio. So I think, as we are here in the imperfect information group, Sugiyama-sensei developed a lot of pioneer work on the density ratio related procedures for machine learning problem, like density ratio estimation and how we compare density ratio for the sort of learning problems. So I'm not going to focus it on this today. Instead, I'm going to talk about this thing called integral probability metric. Instead of the ratio form, we may look at the difference between two distribution P and Q through some test function. And the choice of test function can be a function in a specified function class that best distinguish distribution P and Q. So we take the soup over the whole function class. So this resembles some commonly encountered distribution divergence measure, including maximum mean discrepancy, where we choose this H to be the reproducing kernel Hilbert space, I'm going to talk about it in a bit. And Wasserstein distance, while we choose this H to be one Lipschitz function. And also Kolmogorov, if we are familiar, if we choose it to be a half-line. And if we choose it to be an all-measurable function, we get back to a total variational distance. So in picture, we basically compare distribution either through their difference or through the ratios. So to be more specific, I'm going to talk about integral probability metric as well as how we develop interpretable testing from it. The first set of sort of divergence I want to introduce is this kernel method as well as the maximum mean discrepancy. So looking back into the same form, we have the soup of some expectation minus a different expectation through some function. How can we compute the soup, or what is the appropriate choice of this test function class H can sometimes be tricky depending on what kind of task we are working on. So here I'm going to introduce this kernel method by choosing this H to be something called reproducing kernel Hilbert space. So to be short, the interesting part or the interesting properties I want to introduce is the inclusion property, where one of this, so this K is a bivariate function, where once we take one of the arguments, it is a function in this class. And the other thing is the reproducing reproducing property, where any function in this function class can be written as the inner product of this function as well as the feature map, we call it, or the sort of like a kernel function on a particular point X. So this makes some interesting or nice computational properties for this particular divergence. So this is basically saying this is the RKHS, we call it. And this probably compiled wrong, sorry. This should be MMD, and this is MMD square, so ignore the left part. So basically, we want to say this, if we have this particular soup on the RKHS, this can be written as the function of expectation on Kx, where x comes from P, versus the function that comes from Q. So there's a Q here in blue. I should compare it better. So this is a quadratic form that we can compute. Think about if we have a sample form from P and Q in a two-sample testing sort of framework, we can empirically estimate these expectations and get this in closed form. So moving beyond, there's another interesting integral probability metric that is based on Stein's method, and we have this thing called kernel-Stein discrepancy. So this was adapted by Stein's, Charles Stein's idea. That is a different one from what Matsuda-san talked earlier. So the one Matsuda-san talked about is 1956, and this one is 1972. So Stein's original idea is to ask how far is the data from a normal distribution. So it's used for normal approximation. While if we want to measure the difference of some random variable x from a different distribution Q, then we can just take this soup over some function class on a Stein operator, what we call it, that is specified as f prime minus xf. So this is a specific Stein operator for the Gaussian or standard Gaussian distribution. Extending this sort of normal approximation to a general case, as long as we have an operator TP that satisfies this thing called Stein's identity, we can use this as to define a Stein discrepancy. Again, this is also an IPM form, while this is expectation on Q and the expectation on P, and take their difference. Just that instead of a function on its own, we are putting a Stein operator on some function of choice. And this function of choice we have here is also the kernel function or the RKHS function. So as simple as that, because we can take the decomposition in terms of inner product, we will find this particular f star and have this quadratic form. So this will also have a similar sort of computable form. Also, the nice thing is that the HP here only depend on the model P, and the Stein operator we're using will surpass normalizing constant. So we are able to deal with the sort of like unnormalized model, as Michael mentioned earlier on his talk. Why is this so? One particular choice of Stein operator is this Langevin Stein operator, which take the score function with the product of score function and the f, as well as derivative of the f. So in this case, this operator only access the density P through its score, so that we do not need a normalizing sort of constant. So just to recall the previous example, this ZF is actually taking log P, the score of standard Gaussian. What I want to point out here is the Stein operator is not unique. You don't need to choose this particular one. There are different ways to construct Stein operator, and they may or may not perform better in different tasks. So this is really a user choice, and there are interesting studies and systematic ways to analyze and develop these. So when I talk about interpretable testing, as the picture shows in the Chicago crime data, it was a particular point or particular location that help us to interpret how does P different from Q the most. So intuitively, one way to interpret or one way to perceive that is when we take a particular choice of H from the whole RKHS of choice, this is what we distinguish between P and Q. The location-based sort of interpretable testing is to choose a particular function. For example, if I just want to take one most different location. This location is basically in the set of this function. So this is, this is x1 to xn. So this is really xn here. So basically, this is the function on the features of observed data. And this technique applied for both MMD and KSD in the IPM introduced. Back to this particular example. So if we plot these functions as a sort of contour map, we will have a sort of a different value that how we compute it through this particular choice of points. And we have a higher value that indicates, so a darker means higher. So a higher value indicates we can distinguish P and Q very significantly at a specific location. While if it's quite wide, we probably can't do it through this particular choice of divergence measure. So in this case, if we find the darkest points, it is where we distinguish P and Q the most in terms of a location-based interpretable testing. Moving on, from a testing perspective, I would like to introduce this model assessment where we kind of term it a little bit different from hypothesis testing, because in hypothesis testing, we are given a model or we're given a model in some form of distribution. However, these days, we have these generative models. We may not write their distributions, or we may not assume a particular family of distributions to work with or to even estimate with. In this case, we then want to assess how good or what is the quality of a particular generative model. So the inspiration comes from this particular work on exponential random graph model, where we take the distribution of a graph. So here X is a graph, a distribution of a graph in a particular exponential form. And this is also unnormalized because sort of normalizing constant required sum over all possible configuration of X. So the Stein operator looks in a slightly different form that need to loop over all this. again, as I mentioned, star operator is not unique, so you can choose different ones for different purposes. So for this one, we choose a particular one that depends on some conditional distribution. So this particular conditional distribution on this S is the location of a particular edge. This means if we impute an edge on the edge index S and condition on the rest of the graph without looking at S. So this is the conditional distribution we look at to construct this Stein operator for exponential random graph models. In this particular form, with the choice of network statistics, this particular conditioning is equivalent to condition on some summary statistics or network statistics on graphs. This is where all it comes from for our sort of interpret testing for generative models. Again, if we think about this as an exponential family, the same sort of like perspective will also hold. So what do we mean by assessing the quality of generative models? We want to say that if we are given a trend sort of generator, we can't have a density or we can't have a sort of distribution family from it. All we can do is to generate samples, and we want to compare whether this is the same or whether some given observation come from this particular generative model. So there's no explicit distribution, and the sample can be very imbalanced. We may generate way more samples from the generative model compared to our observations, so that we do not want to use the standard asymptotic test. So here, what we want to do is, instead of we are given the conditional distribution when we have the model P, we estimate this conditional distribution. Then we find this conditional score accordingly. This is not only applicable for graphs, this is also applicable for Euclidean data as well as other data scenario like Riemannian manifold or spatial temporal data. So in this case, we can think about the interpretable feature via this summary statistics T of choice. If this test can help us to distinguish the data distribution versus the sort of generative model, then we probably can think about this summary statistics is a good indicator or is a good signal to help us to distinguish these two models. If not, all we can say is this particular test statistic does not help us to distinguish these models, but we may not have characterization, meaning that P equals to Q in this particular case, because we do not know the family of distribution we may have from the trend generative model. So these are some of the borrowed idea from hypothesis testing, but some of the sort of drawbacks we do not have in terms of statistical guarantees. So in the last few minutes, I want to talk about some of these framework may apply to the foundation models and some of the existing and future works. So for this test statistics, we talk about how does we perform hypothesis testing from a statistical distribution to assessing a generative model. So the interpretive testing are based on how we want to distinguish two distributions. They can be location-based or they can be based on summary statistics via the conditional distribution. So this is how we, also why we care about this maximum mean discrepancy as well as the kernel-Stein discrepancy. The next question becomes, can we also use this test framework to tackle some of the issue on the foundation model, especially for the security issue, to distinguish whether a set or a model is embedded with some notion of safe, I would say. So safety and security, some people use it interchangeably. I perceive them as active attack and passive attack. So in the context of a large language model, I perceive them in terms of like a testing framework in three parts, where we have the data input, which is our prompt. We want to say whether our prompt itself is malicious, whether we put in some illegal prompt to feed our sort of model. Then in terms of model reaction, we want to see which part of the subnetwork are more activate when reacting to the malicious prompt. So this is effectively a spatial temporal distribution we can embed in and do the testing on. Also, we want to look at output detection while we have a given input, and the distribution of the output may or may not depart or deviate largely from the safe output. So these are the things we may look at when we get into the large language model context. So effectively, we can have these different sort of aspects in interpretable testing for different parts of the input output as well as the model sort of training. Then we may end up having an aggregated score on all this sort of testing result as well as their sort of interpretable feature. These are something interesting to be explored. In the end, I would like to also promote this vision towards building a reliable, interpretable, as well as a human-centered AI system. I think, as Yi mentioned early in the morning about the privacy-aware learning procedure, as well as Michael talked about this model misspecification, these are the sort of interesting direction to explore, also with the context of testing framework. Also, I think maybe Futami-san will talk later about uncertainty-aware sort of treatment on calibration. And for here, because of a lot of data, as Ishida-san mentioned in the talk in the morning, we may not have correct labels, or we may get corrupted data. We may also need to incorporate uncertainty on this, on treating these data. So these are the sort of future directions we may proceed in the next few years. And I would leave some room for questions in case there.
Okay, thank you for the introduction. It's my honor to introduce my work today. Actually, my research focus is not about safety, but I will talk about how the safety involves in the context of robot learning today. So probably my research topic is a bit different from others, but yeah, hopefully, yeah. I would be happy if you are interested in any of my work. Okay. As many of us know, many people are working on robot foundation models, and now that many people are using ChatGPT or something of many LLMs, and also in this context, many people are started to using large models for control robots. So actually, this trend is very nice in the sense that we can control robots through using natural language. And this would make the robot accessible to everyone because it will not require expert knowledge to control robots. Then, so behind the emergence of these robot foundation models, there are two factors. And one is that the model itself scaled significantly. And at the same time, the dataset scaled significantly. So, for example, so one of the popular models has billions of parameters, like 7 billion parameters. And at the same time, we recently have a very large-scale dataset. So, for example, one of them is called Open Cross Embodiment dataset. In this project, we collected nearly 1 million robot trajectories. And in this project, we collaborated with researchers all over the world. So I actually participated in this project. Then, yeah, so we unified the data format and collected all the dataset and then published as a single dataset. Then, yeah, so here is somehow a framework for training large-scale models. So first, we have to collect a huge amount of data. Then, typically, the dataset size could be more than 1 million trajectories. And then we train the model. Then usually the backbone of this kind of robot foundation model is vision language models. And then we deploy it in a real robot. But actually, there are some obvious limitations in this framework. For example, here you can see some videos of the performance of the trained model. Here you can see that a robot grasp on apple and move it to our target region. But still, you can see that the manipulation is very, very simple. So here you can just see a single arm with a 2-finger gripper, and which is very simple. And also, another limitation is limited zero-shot performance. For example, if you bring this model to unseen environment, the model will not work at all. So in many cases, if you want to deploy this kind of models, you need to fine-tune it. So you need to collect additional demonstrations, and then you need to fine-tune the model. But actually, so here, this is a point where we see some limitations. So here, the manipulation is very simple, and if you want to have if you want to achieve much more complex tasks, like using 2 arms with a multi-fingered hand, you would need much more demonstrations. But actually, the correcting demonstration is costly and time-consuming. So far we have already corrected nearly 1 million trajectories, but it's already infeasible for a single laboratory to correct this size of data. But if you want to achieve more complex tasks, then we would need much more demonstrations. That is very problematic. And then also, when we correct the data, we still need heuristics, like, for example, so if you want to learn a single task, then we should use a single demonstrators rather than using multiple demonstrators, because if we include a demonstration from multiple demonstrators, then probably the data distribution will be multimodal, then it's not so easy to learn. So we still need such heuristics to make it work. So the recent studies on braille models showed that the potential, it is great potential, but at the same time, it is obvious that supervised learning is a kind of bottleneck to train braille models. So in this context, I'm recently working on reinforcement learning. So I will introduce these 4 topics today. So I think the 30 minutes is not enough to explain all of the details. So I will just briefly go through each topics, and I would be happy if any of the topics would spark your interest and open the door to future collaborations. Okay, then let's get started. So first I will talk about discovering the multiple solutions in offline reinforcement learning. So these are about the data collections and how to capture diverse behaviors from a static data set. So the answer to the first question, the how to collect the sample safely, is first answer is let's leverage offline data. That's my answer in this first topic. So luckily, we had a great talk about offline reinforcement learning in this morning, so I don't have to introduce offline reinforcement learning probably. But I will just quickly introduce the problem setting here. So in reinforcement learning, so we assume that the system follows the Markov decision process. Then we have some elements like agent and environment. Then here, the policy, which is the conditional distribution of action given state, determines the action. Then our goal is to maximize the expected return under this condition. Then, so here in this talk, I will talk about both online and offline reinforcement learning. So in online reinforcement learning, we iterate the data collection and policy update. So this is probably the more popular and traditional reinforcement learning. And in offline reinforcement learning, we just leverage the pre-corrected data set. We do not go back to data collection, just we leverage the pre-corrected static data set. So this is offline reinforcement learning. And I believe that this problem setting of offline reinforcement learning is very suitable for training braille models, because when we train this large-scale models, we assume that we have a large-scale data set. Then collecting a few demonstrations does not change the scale of the data set, and then probably it would make sense to first fully leverage the large-scale data set. Okay. Then in the first topic, I will talk about discovering multiple solutions in offline reinforcement learning. In reinforcement learning, it is actually well known that there can be multiple optimal solutions. For example, if we make agent at a certain speed, if we make the agent walk at a certain speed, then there can be multiple walking style, like hopping or just stable walking, or it could be anything. So there can be infinitely many walking style. Then probably if we could discover multiple solutions beforehand, then probably we can quickly adapt to a new environment or new task just by picking up the learned repertories. So that's the goal of discovering the multiple solutions. Then, so when we learn multiple solutions, there are many ways to model it, but I think a typical way to model multiple solutions in reinforcement learning is to learn the latent condition policy. So in standard reinforcement learning, we have a policy like this. This is just a conditional distribution of action given state. But we decompose this policy into this representation. Then here, this part represents a policy condition to the latent variable. And this policy shows the different behaviors with the different values of the latent variable. Then this part shows prior distribution. And typically we use uniform distribution because we want to have an equally good behavior for different styles. Then when we train this policy, typically we maximize this kind of objective function, and this is usually given by the sum of the task-related reward term and the diversity term. There are many ways to maximize these objectives, but in this work, I focus on reinforcement learning algorithm to maximize this objective. So in my prior work, I worked on this approach, and then in my prior work, we use this kind of objective function. So here, this is the expected return given the latent variable, and also this is mutual information between the latent variable and the state action pairs. And this mutual information term encourages the diversity of the learned behavior. And also this term encourages the policy to achieve the high score in a given task. Then, so here you can see the visualization of the working style. So as I said, so here this is a result of the offline reinforcement learning algorithms. So in this learning, so we use a data set that contains the diverse behaviors. Then, so here you can see that policy changes the behavior according to the value of the latent variable. So you can see the difference of the joint, but still the agent or hops in a certain same direction. The challenge of this kind of offline reinforcement learning is to find how to learn the latent variables. So the latent variable corresponds to the latent space of the skills in practice. Then, so in this work, we use a kind of EM-like procedure. So first we fix the posterior and then optimize the policy, and then we fix the policy and update the posterior. So we iterate this process. In this way, we can learn both the latent space and policy. So here, this is a kind of the visualization of the learned policy. So in the toy task, so here, the task is to plan a trajectory from here to here. And then this latent variable shows the different path according to the value of the latent variable. And also you can see the value of the latent variable assigned to different state action pairs. And in this way, we can learn different walking style. So this is another example on the Walker 2D. So here you can see the one-leg hopping, and this here you can see the walking standard, kind of standard walking style. And once we have diverse walking behavior, so we can quickly adapt to the change of the embodiment. So here is an example of the adaptation. So this robot has a different embodiment, which is different. The embodiment which is different from the one used for the training. And then, but still, so we can quickly adapt to the new embodiment just by picking up the learned policy. And one interesting aspect of learning the diverse solution is that this diversity improves the quality of the policy in some cases. So here, so in this work, we constructed our own data sets that contains diverse behaviors. Then, so here it shows the result of using the standard offline reinforced learning algorithm that does not consider multimodality of the solution. Then, so here you can see that very famous methods like implicit Q-learning or TD3BC does not work well for this data set. But our method consistently showed high performance in these domains. So I think that this is very interesting. So if the data set has a diverse behavior, sometimes the performance of the monolithic policy drops. And then so we need to cope with this data set diversity, we need to think about how to learn the latent space of the scale. And then I believe that this can happen in the large scale training as well. So if we have 1 million data sets and collected by the different laboratories, this should naturally contain diverse behaviors. And then, so when we train large scale models using the open cross embodiment data set, what happens is that performance of the model was just, success rate of the task was usually 70% or something like that. So we could not achieve the 100% success rate even if we employ the model in the trained environment. So I believe that there are some issues related to the model solution diversities. Then I think this kind of approach should improve the performance of the vision language models in a larger scale. Okay, then let's move on to the second topic. In the first topic, I just used the data set from a single robot. So we did not include the data from the different multiple robots. But in the second topic, we actually worked on this cross-embodiment of offline reinforced learning. So typically, the D4RL dataset, some many famous benchmark dataset contains data from a single robot. But we constructed a dataset that contains motion from different robots with different embodiment, like the humanoid or dog robot or something like that. Then we performed investigate how offline reinforced learning performs in this setting. Then in this work, we use a kind of special neural network architecture. So this is developed by other groups, but so this network architecture is designed to deal with variable length, state, and actions. Then, so here is one of the empirical results on this dataset. This row corresponds to the performance on different robots. And then this column corresponds to the result of performing the offline reinforced learning for each robot. And then, so this column corresponds to the cross-embodiment offline reinforced learning using the entire dataset. Then, so here, this AXP shows the result of using expert data, only expert data. Then here, this 70% corresponds to the result of using the dataset that contains a suboptimal data. Then when we use just an expert dataset, the effect of the cross-embodiment learning was very minor. So we did not see the big difference between the performing the offline reinforced learning for each robot and cross-embodiment learning. However, if we use a suboptimal data, then we see the obvious difference. So this is a result of performing the offline reinforced learning for a single robot, for each robot, and this is a result for performing the offline RL for entire data simultaneously. Then here you can see the performance improvement here. So this indicates that there are positive transfer when we perform the cross-embodiment learning. At the same time, we also observed negative transfer. So here we observed a performance drop from here to here. Then, so this means that there could, in cross-embodiment learning, sometimes the performance harmed to some extent. So then, based on this observation, we analyze the cosine gradient conflict or cosine gradient similarity. So this is actually visualization of the similarity of the, this is a visualization of the embodiment similarity. And this is actually the visualization of the gradient similarity. Then, so actually you can see the correlation between the embodiment similarity and the gradient similarity. So here we thought that gradient embodiment similarity is created with a gradient conflicts. Then we employed group-wise update. So to mitigate the gradient conflict, we employed a group-wise update. So here, so we made a group of the similar embodiments, and then we separately performed the policy updates in a batch. So in one batch, we just updated this. We update the policy based on just this group, and then in another update, we just update the policy using the sample from this group, or we did it in this way. Then actually we obtained a significant performance improvement. So this approach is very simple, but I believe that this is very promising direction to go. So once we obtain the model pre-trained in this way, we can quickly adapt to unseen robots quickly in online reinforced learning. So, well, I think in near future, probably we would have a foundation model that controls any robots. But I think that it's not so easy to insert foundational models just from the demonstration data. So our aim is to develop such robot control foundation models using offline reinforced learning. Okay, then let's move on to the third topic. So far I just talked about offline reinforced learning, but we are also interested in online reinforced learning as well. In online reinforced learning, now that many people are using a massively parallel environment shown in this figure. So NVIDIA has developed a nice simulator called Isaac Gym or Isaac Lab. And then here we can use parallel environments like 20,000 or more than thousands of environments in parallel. But actually, most of the reinforced learning algorithm was originally developed for a single environment. Then actually the learning dynamics of such algorithms may not be suitable for massively parallel environments. So we investigated, so what would be the best algorithm design for massively parallel environments? And so actually, so previous studies have already shown that simply employing the standard reinforced learning may not work well in some tasks. For example, probably many of you know the PPO, which is used for fine-tuning LLM. But if you just employ PPO for this domain, sometimes PPO does not work well. So this is a learning curve of the PPO, and the PPO doesn't learn this task properly. Then in this work, we investigated leader follower framework. In the leader follower framework, we have a main target policy, and also we have a follow-up policy which is slightly different from the main target policy. Then in this way, we can parallelize the data collection and then efficiently explore the state action space. And this leader follower framework was proposed by another group, but we investigated theoretical aspects of this framework. And then in our work, we showed that actually the distance between the leader and the follower matters significantly in this framework. So if the distance between the main policy and the follower policy is too large, it will increase the bias in the policy gradient. And also it will reduce the efficient sample size. Then, so we need to think that we thought that it is very important to somehow regulate the distance between the main policy and the follow-up policy. Then so here is the result of or performance of our proposed method. So this red curve shows the learning curve of the proposed algorithm. Then so we obtain the consistently good performance across tasks. Then yeah, so we are going to extend this algorithm for larger model, for training the larger models with much more multitask domains later. Okay. Then yeah, so then at last I want to talk about a little bit about how we should deal with the distribution shift. So probably many of you are interested in this topic. So I'm not actually an expert on distribution shift, but we somehow adapt the techniques for domain adaptation in the context of robot learning. So in offline reinforced learning, so we are interested in learning a policy that takes image as its input. But the problem is that if the background of the agent changes, then the policy cannot perform well. So the goal is to obtain a visual encoder that is robust against the change of the background or something. So typically, the visual encoder gives embedding for different image input. Then typical visual encoder gives different values of the latent space. But what we want to do is that if the state of the agent is the same, we want to obtain the invariant feature, even if we change the background of the image. Then, so to achieve this, we employed some domain adversarial technique. Then we obtained a robust policy that works robustly, even if we change the background of the agent. And we also employed the same technique for the imitation learning as well. So in the imitation learning, we assume that the demonstration data is given, and then we train a policy to mimic the expert behavior. Then, so here in this training, what we do is that we have the data from the expert, and we perform the data augmentation. Then so we train the visual feature extractor in a way that it outputs the invariant visual features, even if we change the data augmentation style. So in this way, we obtain a visual extractor, which is robust against the change of the data augmentation. Then afterwards, in the second step, we just take the initial image of the target domain. So we thought that it's unfair to perform the policy under the target domain as well. So we just take the initial picture before executing the policy. Then we perform the additional training of the policy. So we try to obtain a feature extractor that outputs the invariant feature for the demonstration domain and target domain. Then we also do the policy training as well. Then in this way, we could obtain a system that can work in a different lightning condition like this. So here, typically, the demonstration is performed in one of the domains. Then, so if you change the lightning condition or change the color of the background, or if you put the obstacles, then the policy will not work well. But if we use this kind of domain adaptation technique, we can obtain a policy that works across the different domains. Okay, so this is the end of my talk. So far, what I showed today is just about the result using a relatively small scale of models. Just at most, the model have just millions of parameters. But now we are working on training the model with billions of parameters. So hopefully we can show the much cooler results in a few months. Okay, thank you for listening.
Thank you so much for your interesting talk. Are there any questions from the audience?
Thank you, Professor, for your great talk. So I have a question about your third work on the online reinforcement learning. So in Europe's 2025, there is a base paper of reinforcement learning that they just make the neural network into over 1,000 layers. Yeah, I think you read that paper too.
Yeah.
So, and the results is very amazing that within the same environment step, their results can beat the like a PPO, SAC with a huge gap, right? So I was thinking if it is also possible to include other tasks like a massive environment in parallel to also make such a big gap. Like if we can use the similarity between tasks, then we can also use the knowledge from other tasks to improve the current task to make such a big gap. Is it possible?
Yeah, that's a great question. Actually, well, as far as I know, so it is, some people say that if we increase the model size, the gradient conflicts might be less impactful. So it might, so if increasing the model size might help, may mitigate the problem, but I believe that still we have the gradient conflict during the training. So for example, when we train the VLM models, we do not have such mechanism to mitigate the gradient conflict, and as a result, we do not have 100% success rate, even if it's in the training environment. So I believe that techniques like what I presented today should be implemented to cope with the gradient conflict between the multitask settings.
Thank you.
Yeah, thank you for the question.
Are there any further questions? Okay, so if there is no further question, let's thank Dr. Takayuki for his interesting talk.
Thank you.
Thank you for the introduction. Hello everyone, I'm Futoshi Futami from Osaka University and RIKEN AIP. Today I will talk about the calibration in classification. Usually I am working on the Bayesian inference or some kind of encoder models like the VAE, and my interest is really in the evaluation of uncertainty of those models. And I think the calibration is a bit different from the uncertainty of the Bayesian, but understanding calibration, understanding this kind of concept enhance our understanding how we can interpret or use the uncertainty in our statistical models. And calibration is a kind of the concept which quantifies the reliability of our prediction of classification models. Today, I will talk about some kind of gentle introduction to the calibration methods. As you know, deep neural networks are successful even in the classification problems. And these models usually output the predicted probability first and then select the prediction class, for example, by taking the argmax of the predicted probabilities. And this kind of predicted probabilities are highly useful when making the decisions in high-risk taking scenarios. For example, you can consider the medical diagnosis, such as for example, cancer recurrence prediction. If we can estimate the probability of the recurrence, we can make the better treatment decisions, for example, deriving the optimal threshold for the treatment. And when deriving such optimal decision, we can utilize this kind of predicted probabilities. Usually, we want to use the underlying true distribution for deriving the decisions, but of course it is unknown. We use this kind of predicted probability as a surrogate to make such decisions. And also, this is the different example. Calibration is often used in finance, but I will skip this slide. In this kind of setup, we use this predicted probability as a surrogate of the true distribution. We hope that the predicted probabilities will approximate the true underlying probability. And this concept is elaborated by the notion of calibration. calibration calibration intuitively means how well the model's predictive probability aligns with the underlying distribution. Let's consider the binary classification, for example, where the label is 0 or 1, and we have our hypothesis FW, which outputs the predictive probability 0 to 1. This implies that this score implies that when the input x is given, then this model believes that the probability of level being 1 is this score. And then calibration is defined in this way. Observing the event that our model outputs the score p, then we hope that the actual level frequency, that is the conditional probability, equals to p. Then if this holds for almost surely, then we say that the perfect calibration is satisfied. But unfortunately, this condition is very strong, and modern neural networks are often not calibrated. Let's see some very simple example. This is the very simple neural network, which is the ResNet, and this is kind of the reliability diagram. And let's see around here, in this horizontal line, this corresponds to the confidence. So this corresponds to the score of p. And let's see around the 1.0. Here, blue line corresponds to this frequency of the level. So this blue line corresponds to this conditional probability, and it is nearly 0 to 1. So around here, this means that the confidence value is much larger than the actual level frequency. So this means that this model is suffering the overconfidence. So in this way, many types of neural network shows the overconfidence, or for example, some types of the graph neural network shows the underconfidence in common. And what is more interesting is that the high accuracy does not necessarily imply good calibration. And a well-calibrated model does not necessarily imply a high accuracy. So I think the research about calibration has two important directions, I think. One is how to evaluate the calibration performance. That is, how to evaluate this discrepancy accurately. As I will explain later, this is not so simple. And the second research topic is that how to correct uncalibrated model. So I think this problem can be decomposed into two sub-problems. That is, to understand when our models are well calibrated and also shows the high accuracy. Also, of course, we want to develop the efficient algorithms. That is, when correcting our model, we do not want to retraining our model. We want to apply simple post-processing method to correct the calibration performance. And let's start from this first topic. So I will explain how to measure the degree of calibration. I will explain the simple problem settings. That is, we have some data set, and we split it to the training and validation data or test data. And we use this training data to run our hypothesis. And we use this validation data to measure the calibration. And as I said, what we want to do is to evaluate the discrepancy from this ideal relation. And to do that, I think the most widely used metric is the expected calibration error. It is often called as the EC. And as you can see, this is just the L1 distance between the conditional probability and our hypothesis. And so what we have to do is to construct some estimator by using this validation test data set. To do that, actually, I think there are many approaches, but I think the key to construct the estimator is how to evaluate this conditional probability. To do that, I think one of the most widely used approach is the binning EC. So in short, binning EC considers kind of the local empirical average of the level to approximate this conditional probability. So the binning estimator is given as follows. First, we split the 0-1 probability interval into B small regions. They are called as bins. And then we take the empirical local average inside each bin. For example, for here, y bar is the empirical average of the level in this way. And then we consider that this is the approximation of this conditional probability. And by taking the aggregation between among the all bins, we get the binning EC. I think this binning EC is the most common approach. And for example, when you're using the PyTorch and call the EC metric, this kind of estimator is called. And since this is the estimator, we want to know how much bias we suffer by using this finite sample. Actually, as you know well, by assuming the some continuity, we can decompose the bias into binning bias and variance. We can derive this kind of order. Anyway, now we have the binning EC. We can evaluate this EC by using these samples. And then once we evaluate the degree of calibration, the next step is how to correct uncalibrated model. That is, if our model does not show the good calibration performance, we correct it. And however, as I said, we do not want to retraining our model from scratch. Instead, usually we consider the recalibration process, which is the post-processing approach. That is, we prepare some kind of post-processing function eta, and then using this, and then we use some independent recalibration dataset to run this eta, and then for the final prediction, we use this kind of composite function, and then we hope that our corrected model eta circle FW shows the good calibration performance. And traditionally, many types of recalibration methods has been proposed, including the Plateau scaling or temperature scaling or something else. Actually, recalibration is a running problem over the recalibration data. So we need to answer the following question. That is, if our model shows the good calibration performance over the recalibration data, how about the unseen test data? This is a kind of the problem of generalization in a sense of the calibration. And we can analyze this kind of calibration problem by combining the bias analysis and some kind of statistical learning theory. Here, for example, if we assume that our hypothesis, our recalibration function belongs to some, for example, parametric function, using some kind of covering argument, we can get this kind of order. Actually, this is just the theoretical result, but by developing some efficient generalization bound, we can use this kind of theoretical analysis to develop the new recalibration algorithm. For example, in last year, we derived some kind of Pak-Bayesian method, Pak-Bayesian generalization bound for this expected calibration error. And some of you might know that the Pak-Bayesian approach is very nice to analyze the Bayesian method or probabilistic method. And so we derive the generalization bound of Pak-Bayesian style for the EC. And we derive the new variation inference for the Gaussian process to control the generalization and calibration performance simultaneously. But this is a bit too complicated. I will skip the detail. So far, I was focusing on the binning EC, but it has been reported that binning EC and EC has many drawbacks. And I think from the practical viewpoint, the most largest drawback is the binning EC is very sensitive to hyperparameter. Here, hyperparameter means the size of bins. Usually, for example, if you use the EC of PyTorch, I think the bin size is usually set to 10 or 50, but actually we should select it depending on the smoothness or dataset size. But of course, we cannot derive such a optimal choice of bin size in practice. But unfortunately, EC is very sensitive, so it's very difficult to select. So nowadays, many research try to find out the alternative metric to evaluate the calibration. And there are many types of alternatives, but I think the most promising alternative is the smooth calibration error. Here I cite the 4 years ago's paper, but originally this was proposed almost 10 or 15 years ago. But anyway, smooth calibration error is defined in this way. It looks awkward, but intuitively, this measures the calibration by taking the inner product between the test function h and the deviation between the level and our output score. And this test function comes from the Lipschitz function class. And in different words, this smooth calibration error measures the how much we can detect the miscalibrated direction by using this Lipschitz function class. And it has been reported that this metric has a better property compared to the EC or binning EC. And interestingly, by replacing the function class of H from Lipschitz function to, for example, RKHS or to the polynomial function class, we get the many fancy metrics, which may be used in the fairness field. And then this is the population static. And if we are given this kind of sample, the finite sample estimator of this smooth C is given in this way. And here, primum exists, but this is just the linear problem. We can solve this efficiently. For example, you can use, for example, in Python, you can use the civxopt or scipy or something. And this can be solved order n. So this metric is nice from the viewpoint of the computational cost. And also, compared to the binning EC, without the smoothness assumption, compared to the binning EC, this smooth C has this kind of property. That is, the bias is much better than the binning EC. So this is more nice metric. And nowadays, people started to use this kind of metric. Today, I will not talk about, but the multi-class version of this metric is not suggested from the computational cost, but that kind of discussion is very involved, so I will skip it. So, so far, I introduced the metric focusing on the binning EC and smooth C. And now I move on to the different research question. That is, when we can achieve the high accuracy and well-calibrated model simultaneously. As I said, high accuracy does not necessarily mean good calibration, and well-calibrated model does not guarantee high accuracy. To see this, let's consider this kind of simple model that is just output the class prior. Of course, this is completely useless for prediction because it neglects the input feature. But by definition, this achieves the perfect calibration. So calibration and accuracy is not the same. And to understand when we can achieve high accuracy and well-calibrated model, I don't have the definitive conclusion so far. But recently, we analyzed such situation by focusing on the function gradient, which I will explain now. In that analysis, we focused on the smooth calibration, and we decomposed the smooth calibration into the like the usual generalization analysis to the smooth calibration error over the training data set, which is used to train F, and the generalization error in a sense of the smooth calibration error. And then we separately analyze these terms. And as for this generalization error terms, by developing the usual statistical learning theory, for example, this generalization error can be upper bounded by the complexity of Lipschitz function class. This comes from the feasible set of the definition of this smooth calibration error. And the complexity of our hypothesis. Usually it is the Rademacher or some kind of the Dudley integral. So this is like the usual analysis. And the interesting point is this first term. This is a bit complicated, but so I will skip this. Interesting point is how we control this training smooth calibration error. Here we focus on, as I said, we focus on the function gradient. And in this analysis, we focus on the binary classification setting and focusing on the cross entropy loss. And here F is our hypothesis. And in this setup, we have the logit function G, and this logit function is converted to the probability by using the sigmoid function. And by some calculation, we found that the smooth calibration error can be controlled by the function gradient over the training dataset. Here, function gradient implies the gradient with respect to the logit function. Actually, this is the function gradient over the training data, so this is just the finite dimension problem. But we can extend this to infinite version. In that situation, this function gradient is replaced to the Freshe derivative. But I will skip that. And this implies that if our learning algorithm controls the function gradient, then there might be a hope that we can analyze the training smooth calibration error. And by analyzing the generalization error, we can upper bound the smooth calibration error in a whole. Then, as you might know that the most famous algorithm that controls the function gradient in machine learning is the gradient boosting. You know that the gradient boosting iteratively updates our hypothesis by approximating function gradient at each step. Here we focus on the gradient boosting tree. This G is the logit function. And at each step, we update the logit function by adding the new base runner, which approximates the function gradient. Here, W is the step size. Actually, this psi. Psi is the base runner of our gradient boosting method. And this psi is chosen by solving this kind of optimization problem at each step. And in many implementations of the gradient boosting, for example, in this setup, we focus on the cross entropy loss, but usually we consider the quadratic upper bound of the cross entropy loss. So at each step, we minimize the regression problem of the function gradient. That is, we solve the finite dimensional, we approximate the function gradient by using this base runner. And here, this base runner is taken from the shallow regression tree. And then we iteratively operate our logit function. And then in this setup, we found that by adding some margin assumption, we found that we can achieve the epsilon small smooth calibration error. Here, epsilon usually takes the very small positive value. By setting for example, iteration of the gradient boosting or iteration of the step size or sample complexity. In this way, we can achieve the epsilon small calibration error. Interestingly, this complexity corresponds to the existing well-known multi-calibration boosting algorithm, but it is but multi-calibration is outside today's topic. I will skip it. And also, under the same assumption, we can also assure the misclassification rate. So, and as far as we know, this is the first result that simultaneously guarantee the calibration and misclassification rate for the gradient boosting tree. So this is the more formal statement, but I will skip that. And by leveraging this kind of analysis, we analyze several types of algorithms. For example, we analyze the kernel boosting, which was introduced as some kind of the interesting concept to understand the early stopping phenomena in the kernel regression problem. Or we also apply our technique to the to analyze the two-layer MLP using the neural tangent kernel method. Yeah, but the result is complicated. I will skip the explanation. So far, I've explained the EC and smooth calibration error and some of our recent analysis about the calibration error. And so far, I do not mention about the calibration in a multi-class setting. Actually, it is known that the calibration in multi-class problem is much more difficult compared to the binary classification problem because usually we suffer from the curse of class size k. Usually, if we consider the simple extension of the ECE, we suffer from this kind of bias in a simple binning approach. And other than this, if we consider the simple extension of the smooth calibration error, it has been reported that we cannot solve that kind of problem in a polynomial time. So how to evaluate the calibration in multi-class setting is an active research, still active research field. And also, today what I didn't explain is the notion of the multi-calibration. Calibration is a kind of the concept which takes the expectation over all domains. But in practice, we hope that such kind of the probability approximation probability holds for every subpopulation in the distribution domain. In such a case, technical concept of the multi-calibration is quite useful. But it has been not known the optimal algorithm for this multi-calibration. So developing the efficient algorithm for this kind of problem is still an active research field. So that's it for my talk. Thank you for listening.
For the nice talk, any questions from the ground audience? I have a question for the earlier part of the talk. I think in the morning, Ishida mentioned this estimating limit of the base risk. I was wondering, was this calibrated predictor corresponding to that limit?
You mean here?
Yeah.
It's not. For example, as I explained, for example, by substituting the class prior distribution as the hypothesis, which only, for example, which only outputs if we consider this kind of a hypothesis, then by definition, this satisfies the definition of the perfect calibration.
Yeah.
So in that sense, other than the Bayes classifier, perfect calibration is achievable. And Bayes classifier can achieve the perfect calibration. So they are not the such limit is not equivalent to the perfect calibration. I think perfect calibration is a more easy problem compared to the Ishida-san's limit.
Right, so maybe I should rephrase my question so that in this particular case, with calibrated model, so I think one thing about, let's imagine we have a simple problem. The limit in base risk is somehow achievable for the best kind of model to be fitted.
Yes.
While if the problem is simple, we would probably want to fit a relatively simple model that is in F. And the overconfidence you introduced earlier on was probably have a much higher accuracy but not calibrated. So in that case, that is kind of different if we compute the base risk with the with the trend predictor. So that would somehow be below the base risk if we have some overfitting with finite sample. What I want to ask about is if we are in a calibrated setting, meaning that the F for prediction is the just right complexity in terms of function, then would that be corresponding to how we derive or how we write out the limit for base risk? If I have a calibrated predictor and I'm achieving some form of the base risk limit, do I automatically get this just right notion for model complexity?
Actually, if you have the base classifier, this is satisfied, but in your
not the other way around. Yeah, I was actually asking the other way around.
Yeah. Actually, I have never thought about that. So please give me time to consider how what can we say about that condition. Please discuss later.
Right. So yeah, we can discuss offline.
I think that will be a very interesting question.
Yeah, we can talk more offline. Is there any question from online? No. Great. Let's thank the speaker again.
It's a real pity I can't be in Japan this time, but I really enjoy the workshop. I think it's been really important for me to see how the RIKEN operates, see a bit more background, and see how much there is in terms of joint interests and overlapping interests. And I think hopefully this talk will also feed into this general feeling that there's a lot that we have in common, a lot of themes we are interested in. So this is a brief overview. So I'll talk about synthetic networks, what they are for, present a method for generating synthetic networks, assessing the quality of a network generator, and then say a little bit about science method for anomaly detection. This is based on joint work with Anum, who's a doctoral student just finishing in Oxford, Nathan Ross in Melbourne, and Wenkai, who is the host. And he's actually done good work in preparing the setting for this talk. So what do I mean by networks? I don't mean by network a neural network. I just mean a really maybe a social network. So here's an example of a network between families in medieval Florence, and each family is connected by an edge if there is a network, a marriage relation between them. And so you might see that the Medici family has quite a lot of marriage relations, and the Strozzi family has quite a lot of marriage relations, but there's no marriage relation between the two of them. They were actually arch enemies at the time, so it makes sense. And the social networks scientists actually devised this data set to look at the rise and fall of the Medici family, and they look at the marriage relations and then relate them to business relations, for example. This talk is about synthetic networks. I've just shown an example. So a network is a social network for me, for example. So, or a network of financial transactions. I had a project with a bank called HSBC where we looked at trying to detect fraud in financial transaction networks. So it's not neural networks, it's just real networks. Why do we need synthetic networks? Well, we need it for statistical inference, and we've seen a few examples already for that today. HSBC wanted to have synthetic networks for method development. So because they just wanted to have something that had the same field as the actual data, so that their internal software engineers, for example, could develop software for analyzing these data. They're also used for data augmentation. We've seen data augmentations in the MCMC setting today. They are used for data privacy. HSBC wanted to have a private data set because they cannot ever share their transaction data set. And they are also, of course, used for training generative models because we are running out of real data fast. Okay, so synthetic data, are they easy to make? So here are three networks, which on the face of it, they look quite different, but they are just different visualizations of the actual same underlying network. And that's, of course, not what we want. What we want is that the synthetic data, yes, they should be faithful to the distribution of features that we are interested in the network, but they should also be different enough from the original network to provide variability or privacy. And if we want to do explainable AI, we also want to have theoretical guarantees to mitigate risk and to assess the resilience of the network. What even is a network? So for me, a network is has a vertex set V with n vertices. It's got an edge set E. And for simplicity here, we just think of undirected, unweighted edges, no self-loops, no multiple edges, just a simple network. We can represent this by an adjacency matrix, which is entry 1 if there's an edge at UV and otherwise 0. For an undirected network, we only need to look at the upper triangular of this adjacency matrix. So we can just look at all the entries for U less than V. And XUV is 1 then if there's an edge between U and V. What we are interested here is the setting that we've got one real network, one observed network, and we want to generate synthetic data from it. So these are called one-shot network generators. Thinking of the HSBC example, where we have one network of transactions. There have been several methods around in the literature. So an RNN method, a graph RNN, a GAN method, so with a generator and discriminator called NetGAN, cell, which is a low-rank approximation of the graph Laplacian, and digress, which is a diffusion model from Vignac for graphs. Or we could also fit a parametric model to the data and simulate from the fitted model. Just a little bit about these methods. So graph RNN thinks that there's a new vertex arriving and then it creates edges. So it does not reflect the permutation invariance. So it does not reflect that it should not matter in which order the vertices arrive. It very much matters. And NetGAN assumes edge independence, and cell also assumes edge independence. And the digress we've examined separately has a severe issue of mode collapse of diversity. So it basically does not vary very much at all. So, okay, let's think of a parametric network model fitted to the data and simulate from the fitted model. The easiest one we could think of is probably one where we got independent edges and all edge probabilities are the same. So that's the Bernoulli random graph or Eddy-Schwenny random graph or ER. One step further is that each vertex might have a feature vector and the probability of an edge between the two vertices U and V depends on the two feature vectors. And we've seen examples of that today. An issue is that edge-independent models often generate networks which are not faithful to the original data in the sense that they have many fewer triangles and squares than the input network. And often it's triangles that or squares or motifs of that type that we are interested in, for example, in fraud detection. So another parametric model which Wenkai has already kindly introduced is an exponential random graph model. So an exponential random graph model, we have a simple undirected graph on n labeled vertices, like in the Florentine family network, where each vertex has a family label. And then the model has a scaled count of features in X, so T1 up to Tk. T1 is always the number of edges. And then there's a parameter vector beta. And the exponential random graph model is then exactly what you think it is. It's an exponential model. The probability of seeing the whole adjacency matrix X is proportional to E to the beta transpose T of X. So T is the transpose or linear combination of these network statistics. The normalizing constant is usually intractable, and we've seen that today before. So usually there are cases where we can calculate things. For example, if k is equal to 1, then we have a Bernoulli random graph. We know exactly what the likelihood is. The edge probability, just to alert you, is then e to the 2 beta 1 divided by 1 plus e to the 2 beta 1. So there's a sort of slight translation issue. So the normalizing constant is intractable, but we can calculate the odds ratio of an edge at S, say ij, in the exponential random graph, given all the other edge indicators. And this odds ratio depends only on what's called the change statistic, what Wenkai already mentioned. So only if h is a test function, we look at the change of h valued at x, depending on whether there's an edge at S or not an edge at S. And in particular, so from the odds ratio, we can also calculate the conditional probability of an edge at S given the other edge indicators. That also depends only on the change statistics for the sufficient statistics TL. So that's an attractive feature. And with this feature, we can simulate from the exponential random graph models using Glauber dynamics. So each vertex pair is an independent clock, exponentially distributed clock. When it rings, then we resample the edge indicator for that vertex pair according to the conditional probability of having a 1 there, given the rest of the network, and repeat. So this is a nice way of simulating from the network, creating a synthetic network, but a parametric network model may not necessarily be a good fit. And in particular, if you think of large networks like network of financial transactions, it's very unlikely that it follows a global parametric model like the exponential random graph model. Because the exponential random graph model by default treats all vertices the same, doesn't really have heterogeneities built in. And then we could use black box models like CEL or NetGAN, but they don't really come with theoretical guarantees. So what Wenkai and I were aiming for was to develop a synthetic network generator which naturally allows for theoretical guarantees. And the idea is, so we call this SteinGen. The same Stein was mentioned before in the shrinkage, but also in Wenkai's talk. So we start with a network X on N vertices. We don't assume an exponential random graph model, but we think we have some guess about the conditional probabilities. So we sample a pair of vertices, uniformly, we clear whatever is at this vertex pair, whether there's an edge or not edge, and resample the edge indicator from the conditional probability of an edge given the rest of the network. And then we update and we iterate this R times, and the R output is then the generated network. And this will need to a procedure for estimating the conditional probability of an edge given the rest of the network. I will come to that a little bit later. Just for the theoretical guarantees, here's a photo of Charles Stein, the one with Stein's method with the Stein characterization. And with Stein's method, we can show that this estimation procedure which we use is consistent. We can also show that the Hamming distance between two generated networks is close to that of two independent random graphs. And the mixing time of this Markov chain, which generates the random networks, is of order at most n squared log n. So this is under regularity conditions, which I will also come back to a little bit later. They basically imply that the exponential random graph model is close in distribution to a Bernoulli random graph model, which is not necessarily the Bernoulli random graph model with the maximum likelihood estimate. And that's work which I've done with Nathan Ross. So let's look at how this looks like on a real data set. This is a friendship network on female secondary students for which often an exponential random graph model is used. Here we use statistics, edges, and two stars and triangles. And we compare to two methods which actually estimate the beta parameters using exponential random graph model and generate data from that. We also compare to CEL and to NatGAN. And this is what we find. So on the bottom row is the teenager network, the real values. So the ones which we want to be close to, but not too close to. So we want to have a large Hamming distance, but also something that's close to the observed data. And we see that the density of CEL is pretty much spot on, which is not a big surprise because that's what CEL is designed to do. But the number of two stars, the number of triangles, the number of is far too low, and the number of the shortest path length is far too large. And the Hamming distance is actually fairly small. So they are accurate, but they don't move around very much. The Hamming distance is largest for the parameter estimation methods, but they get, especially contrastive divergence, gets ridiculously high counts for 2000 triangles. And the maximum pseudo likelihood estimator also gives counts which are not really very faithful to what we see, especially compared to SteinGen, which gives a reasonably good density, spot on in the 2 stars triangle shortest path, and also has a fairly large Hamming distance. And NetGAN is a bit of a compromise. So it does, it's not good on density. It's a bit better than cell on 2 stars, but not on triangles. And the Hamming distance is a bit larger. We should also think about how well we can actually do in terms of diversity, because even if we generated a network from the exact same model, of course, the networks would not be exactly the same. So we measure diversity for simplicity by the total variation distance between the degree distribution. So we look at the proportion of vertices that have degree k in the first network and the same proportion in the other network, and sum over all k, and we multiply by a half because it's total variation. In the Bernoulli random graph, we can show that this total variation distance is an expectation approximately as n goes to infinity around n times pi to the minus a half. So it will decrease with n like a square root of n, and there's the pi. And then if you have R-generated networks, which we do in our generation method, we just take the average of the total variation distance and take 1 over the square root of n pi as upper bound. And so here are 2 plots to see how well we do. This is Hamming distance, which measures the diversity, against 1 minus total variation distance, which measures the fidelity. Ideal would be top right corner. And well, I mean, I wouldn't advocate this method if it didn't really do quite well. So you see the crosses for SteinGen for the different iterations of R are really quite high and are fairly close to the theoretical threshold for independent Bernoulli random graphs. A cell is quite faithful, but not so diverse. NetGAN is more diverse, but not so faithful. So now you might say this was on a network of 50 vertices, but we also did it on a yeast-protein interaction network. We did not actually run it for n squared log n time because that would have been too time intensive. But we see that it also does fairly well in terms of these iterations. So how do we actually assess the quality of a network generator? That plays back to what Wenkai already mentioned. We use the synthetic networks, which are generated by the network generator, to estimate the distribution and to develop a Stein kernelized goodness of fit test. So recall, so a Stein operator for a target distribution P is such that for a large class of functions F, which we call a Stein class, the expectation of APF of x is 0. So the expectation vanishes. Then the intuition is that if x is close to W in distribution and x has distribution P, then also for W, the expectation of the Stein operator should be close to 0 if G is sufficiently regular. And one way to find a Stein operator is to choose this operator as the generator of a homogeneous Markov process, which has stationary distribution P. Of course, and there are many choices. And then the kernel Stein discrepancy uses this idea that if P is our target distribution and Y comes from a distribution Q, then the expectation of APF of Y should be close to 0. And here we take the supremum over all test functions F, which are in an RKHS with kernel K. But the beauty is, in this RKHS setup, we know exactly which function takes on the supremum, and we can even write it out. So it's HP of XY. And so in particular, so y and y prime are independent from Q, then the KSD squared is just the expectational HP of y and y prime. So rather than having to find out where the supremum might be, we have an exact formula for it. And then for conditional graph distributions, we can do the same thing as before. Maybe in the interest of time, I might skip this. Well, so we basically do the same thing. So we have the Markov chain has a probability that xs is equal to 1. We go to 1, and with probability 1 minus that, we go to x having no edge at s, and then we have to subtract f of x because it's a Markov generator. And here we look at the conditional distribution of an edge at s given the change statistic which we've observed. And the overall Stein operator is then the sum over all edges of these individual operators. Here's a worked example how we estimate the condition probabilities. It's quite a small one. So here we just have a graph on 6 vertices, and T is the number of triangles. So we have 2 triangles in the overall network. For each vertex pair, of which there are 6 vertex pairs, we have 4 vertices, 6 vertex pairs. We record whether or not there's an edge. So between 1 and 2, there's an edge, yes. So we record a 1. We also record what happens to the change statistic. So if I have an edge there versus not an edge there, what's the change? So without an edge, I would only have 1 triangle. With the edge, we've got 2 triangles. So the change is 2 minus 1, which is 1. 1 and 3, there is no edge. So xs is 0. If there was an edge, we would have 4 triangles because we would have a complete graph. So the change would be 4 minus 2, which is 2. For 1 and 4, it's the same as 1 and 2. For 2 and 3, it's also the same as 1 and 2. For 2 and 4, we have 2 triangles. If we take the edge away, we have no triangle. So we have 2 minus 0, which is 2. So then we make a little table. We look at the different values of the change statistic. We count how often we see an edge and how often we don't see an edge. And the estimated probability is then just the proportion of times that we see the edge. Except if we don't see an edge at all, we have add a little error epsilon. And if we see always edges, we also add a little error epsilon, where epsilon is a very small number. And then we build a kernelized Stein discrepancy based on the Stein operator, and we call this agrast. And because of this modular form that we just sum the operator over all vertex pairs, we can also estimate this operator easily by resampling vertex pairs. Because that way we don't have to look at all n choose 2 vertex pairs, we just look at B vertex pairs. And that still works quite well if B is like 20%. And the RKHS, there are several kernels which are often used. We use mainly Weisweiler-Lehmann or the graphlet kernel. The vertex histogram kernel doesn't seem to be so informative. And using Stein's method, we can again get theoretical guarantees for the consistency of the estimation of the Stein operator, for the asymptotic normality of the statistic without subsampling, and also asymptotic normality for the subsampling procedure. And all these guarantees come with an explicit bound. So they are not just n goes to infinity, but we've got a exact expression for finite n, which depends on the kernel, of course. And so the conditions imply that the graph statistics is pretty much sufficient for the model or close to sufficient, that the epsilons go to 0, and the distribution is close to that of a Bernoulli random graph in a way that we can quantify. And then if we try this on the teenager network on SteinGen, we again find that SteinGen does best compared to the other estimation methods. And here we look at the proportion of the rejected agrast test at 5% level. So 0.6 is a bit larger than 5%. We only have 100 runs, so it's within margin of error. A cell is second best, and the others don't seem to fit very well. Okay, so last, I would like to talk about a little bit of work, how we can use this also for anomaly detection. So for inhomogeneous random graph, where we've got independent edges with probabilities, say PS, we can again build a Stein operator, which is an average over all vertex pairs of the Stein operators, which have go from X to having an edge at S with probability PS, and not having an edge at S with probability 1 minus PS. And then we build a GKSS type statistic, and recall that h of xs prime is where the statistics is taking on the supremum. So this is the GKSS squared. And then we did an experiment where we planted a clique. So on the left, we've got a Bernoulli random graph. On the right is a graph with the same number of edges, but we force a clique to be present. So here you see the clique. So the independence is destroyed. The graph is the same density, but the independence is different. It's no longer valid. And here, if you look very, very closely, you see that in this clique graph, if we plot a heat map of this function h, which tells us where we take the on the supremum, we can just about make up where we planted the cliques. So this is very much related to what Wenkai showed about the Chicago crime data, where you can pinpoint the crimes. It's a similar flavor, but a different use and slightly different twist in detecting these anomalies. So a little bit more work that I've done in this space and also future work. So we looked at a Sagesse, which is a diffusion model, scalable digress really, which had severe diversity issues, which was partly what prompted our emphasis on diversity. We also used Stein's method for differentially private network generation based on spatial data. So that's AI stats. We're looking at other model for random networks, network time series. And we also do this anomaly detection beyond networks. So this is with my student Michal Kosira, that's come out on the archive. Somewhat in progress is scaling. And future for this kind of work, I would like to include node and edge attributes, like to look at hypergraph time series, and also the multi-layer networks should not be so hard. Just to highlight a bit more connection points for statistical safeguarding for AI. So I've already just mentioned differential privacy. I didn't really have time to talk about conformal prediction for distribution-free guarantees. We have a paper on counterfactuals using conformal prediction, and also on data contamination. That's the latter one is with Wenkai as well. And then I also have a line of work on generalization error bounds, which are based on information theory, one for GNNs and the other one for the tilted empirical risk. So these are, and here are some publications. And finally, at the end of June, I'm going to host a workshop on Stein's method and networks. So if you're more interested in this, please think about joining either in person, or we are also trying to set up a hybrid option. Thank you. That's all. I think I've also run out of time. Thank you very much.
It's been a very fruitful day. And firstly, thank everyone for coming for this. I would like to take this opportunity to thank the Aspire program director who talked in the morning, Miyano Sensei, and the RIKEN AIP director, Sugiyama Sensei, for supporting this workshop and the statistical safeguarding program. I would also like to thank Ishida, Futami, and Takeru for organizing the event, as well as thank many of you to be here to attend today. I think it was a great day of a lot of interesting talks, as well as common interests. We saw a lot of playground in RL. I think that's probably the most exciting topic at the poster session, as well as in the talks, and as well as statistical estimation theories, including differential privacy, as well as different ways for shrinkage methods. And there are different Bayesian perspectives presented, and I think there are many interesting discussions during the coffee break. I think I very much look forward to more detailed discussions as well as collaborations. I would also want to mention that this statistical safeguarding program is a 5-year program, and we have the opportunity to exchange for research visits. And if you are interested, feel free to talk to us and establish more detailed research collaborations. And again, thanks a lot for coming, and I would conclude today. Thank you.